Hey everyone, and welcome to This Explainer. Today, we're going to dive into a seriously fascinating mathematical concept that secretly powers our daily lives. You know, if you've ever thought math was just this strict, linear path stretching out to infinity, well, you're in for a treat. We're going to explore a type of math that loops, wraps around, and repeats. So, let's get right into it. Okay, I want to start by throwing a bit of a mathematical puzzle at you. How in the world can 10 plus 5 equal 3? I mean, in standard arithmetic, that's just wrong, right? 10 plus 5 is 15. But what if I told you that in a very specific, incredibly common context, 10 plus 5 is absolutely, perfectly 3? Well, picture a standard 12-hour walk clock. If it's currently 10 o'clock and you add 5 hours to your schedule, what time is it? It's 3 o'clock. We don't say it's 15 o'clock. Once that hour hand sweeps past the 12, it just resets. The numbers wrap around. And without even realizing it, this everyday act of telling time is your brain intuitively doing something called modular arithmetic.
Here's a quick look at our agenda for this explainer. We'll start with number 1, the clock arithmetic hook. Then we'll move to 2, defining modular arithmetic, and 3, the modulo operator. After that, we'll cover 4, congruence modulo, 5, properties of modulo, and finish up with 6, real-world applications.
So let's jump straight into section 1, the clock arithmetic hook, or the math we use every day. You know, it's wild how much of our world is actually governed by cycles. The whole reason our math needs to wrap around in the first place is because of the physical reality we live in. The rotation and revolution of the Earth create these natural periods. Day and night repeat, the days of the week cycle from Sunday right back to Saturday. Even things like plant life cycles and seasons loop every single year. And think about our transportation. Railway and flight timings run on a cyclic 24-hour clock, resetting back to 0000 right at midnight. All of these things require a mathematical model that repeats after a fixed interval. And that brings us to section 2, defining modular arithmetic, and a quick chance to meet the prince of mathematicians. So what is this formally? Modular arithmetic is basically a system of arithmetic for integers where numbers wrap around a specific value, which we call the modulus, right after reaching it. So unlike normal linear math that just goes on forever in a straight line, modular arithmetic processes cyclically. Whenever a number hits that modulus cap, it essentially resets, and we just replace that number with its remainder. And we definitely have to give credit where credit is due here. The really powerful ideas behind the cyclic math were formalized by the incredible German mathematician Carl Friedrich Gauss. His contributions were so massive that he's actually known as the Prince of Mathematicians. He basically took something as intuitive as counting hours on a clock and built this robust, flawless mathematical engine around it. Let's move along to section 3, the modulo operator. Let's break down how we actually do this math. It all starts with something you probably learned way back in elementary school, the basic division theorem. It says the dividend, x, equals the divisor, y, times the quotient, q, plus a remainder, r. For example, if you divide 13 by 12, the divisor is 12, the quotient is 1, and you're left with a remainder of 1. Simple enough, right? 13 equals 12 times 1 plus 1. Now, here's the crucial part, how this everyday theorem transforms into the modulo operator. In modular arithmetic, we honestly don't care about the quotient at all. We don't care how many full times that clock hand spun around. We strictly care about where it ended up. So the formula just simplifies to x mod y equals r. The modulo operator is simply asking you, hey, when you divide x by y, what's the remainder? And that's your answer. Which perfectly sets us up for section 4, congruence modulo. This is all about what happens when different numbers mean the exact same thing. And this is where things get really fun. In math speak, we say two integers a and b are congruent modulo n, and you'll see this written with that cool little 3-line equal sign, if they differ by an integer multiple of n. In everyday terms, it just means that a and b are going to leave the exact same remainder when you divide them by n. Or if you subtract b from a, your result will be perfectly divisible by your modulus n. Let's actually compare standard equality with congruence to make this crystal clear. In standard math, 61 only equals 61. End of story. But under a modulo 7 system, 61 is actually congruent to 5. Why is that?
Because if you subtract 5 from 61, you get 56, and 56 is perfectly divisible by 7. That means in a modulo 7 world, the number 61 and the number 5 are essentially identical values. They land on the exact same spot. Now that we've got the core concept down, let's head into section 5, properties of modular arithmetic, or what I like to call the golden rules. These are the shortcuts that let us calculate massive numbers without pulling our hair out.
First up is property 1. It states that if you take a value x and you increase it by any exact multiple of your modulus y, your final remainder will never, ever change. Just think of it visually. If you add 12 hours or 24 hours or 36 hours to a clock, you're really just spinning the hand in full, pointless circles. You're always going to land right back on the exact same remainder you started with. And that brings us to the wonderfully elegant addition property. This is a total game changer. If you want to find the modulo of two numbers added together, you do not have to add them up into some giant messy number first. You can actually find the modulo of A and the modulo of B separately, add those smaller remainders together, and take the modulo of that. It distributes beautifully.
Let's actually walk through a real example to prove it. Let's solve 14 plus 8 modulo 5. Doing it the traditional way, 14 plus 8 is 22, and 22 divided by 5 leaves a remainder of 2, right? Now, let's use the property instead. 14 modulo 5 leaves a remainder of 4. 8 modulo 5 leaves a remainder of 3. Add those smaller remainders. 4 plus 3 is 7. And finally, 7 modulo 5 leaves a remainder of 2. See? Both methods arrive at exactly the same answer. This is a massive lifesaver when you start dealing with huge computations.
And the best part is that this elegance doesn't stop at addition. As you can see, subtraction and multiplication share the exact same kind of distribution rules under a modulus. You can perform the modulo operation on the individual, bite-sized pieces before subtracting or multiplying them, which keeps your numbers small and super manageable.
Okay, so we've looked at the math. Let's transition to our final section, real-world applications, and explore exactly why this matters. Because I promise you, this is not just abstract theory. It is literally the invisible engine of modern civilization. Modular arithmetic is everywhere you look. In computer science, it's used constantly in bitwise operations and calculating hash functions. In book publishing, it's the exact math used to validate the ISBN barcodes on the back of every single book you buy. In music, the entire system of 12-tone equal temperament, basically how modern instruments are tuned, relies heavily on modular 12 arithmetic. Calendar algorithms use modular 7 to determine what day of the week any given historical date fell on. And perhaps most importantly, in cryptography, systems like RSA encryption use massive prime numbers and modular arithmetic to generate the public and private keys that secure your bank accounts, your private text messages, and literally all secure digital data across the internet. So that brings us to the end of this explainer. The next time you glance at a wall clock to check the time or hit send on a secure text message, take just a second to ask yourself, how much of our entire universe is secretly governed by the cyclical, wrapping power of modulo math? It's literally hiding in plain sight, keeping our world ticking perfectly in time. Thank you so much for joining me today. Stay curious, keep learning, and I'll catch you in the next explainer.